Okay, we're very happy to have Bartosz Wcisło from Gdansk, and so I think I'm better at pronouncing Wcisło at this point, but Gdansk, I'm not sure. So
Gdansk is very good, actually.
So he will be speaking on satisfaction classes with the full collection scheme. So go ahead, Bartosz.
Right. So let me start with saying that, as always, it's an extreme pleasure to speak at this seminar, and thank you so much for the opportunity to do so. Okay. So we'll start. Okay. So we'll start with a couple of definitions, and I believe that normally for this audience, those definitions are not really necessary, but for the sake of completeness and for the sake maybe of people who will see the recording, let me very briefly go over them. So this talk concerns, so the general framework, general question this talk concerns is a question of what kind of properties can be imposed on compositional truth or satisfaction classes over PA, so that the arithmetical content of the theory we get is still not a conservative extension. It's not a conservative extension. So given many properties you can impose on compositional truth, which of them make truth conservative or non-conservative, which of them make the extension remain conservative. So the general framework is this. I mean, I will actually change this framework halfway through the talk, but let me start with like, in order to make it more compatible with the literature on Tarski-Pan theory. So you take PA, you take Peano arithmetic. To this, you add a one fresh unary predicate T. And then you add axioms that stipulate that this T behaves like a compositional truth predicate for arithmetical sentences. So I'll go over the axioms in a minute. So in that way, you get an axiomatic theory. We call it theory compositional truth CT minus. The minus sign stands for lack of induction. So you have PA, in PA you have full induction. In this theory, you only add compositional clauses for the truth predicate. You don't add induction scheme for the formulae containing the truth predicate. Okay. The exact definition will come on the next slide. So this theory CT minus is what you get by adding to PA the following axioms. So if you give me an atomic sentence in the sense of PA, so the equality of two closed terms, it is true if and only if arithmetical values of those terms as computed in the model are equal. So essentially, if you don't if it's not easy to process, just ignore it. So on the atomic sentence, they are true if and only if the obvious truth condition on atomic sentences holds. A sentence is not true if a negation is true if and only if the negated sentence is not true. A disjunction is true if and only if one of the disjuncts is. A quantified sentence, so existential statement, is true if and only if it is true under some substitution of a numeral for the variable. So you can substitute some numeral, you can plug it into the formula, getting a new closed sentence, and this sentence is true for some substitution. Moreover, for a number of technical reasons, we also require that our truth predicates are always invariant with respect to substitution of terms with equal values. So if you give me two sequences of closed terms and you substitute with the same values and you substitute one for another, then whatever you get is then truth does not depend on the exact choice of terms. If you add full induction to CT minus, you call it CT. So CT minus means truth is compositional, CT means truth is compositional and satisfies induction. So the whole motivation for this research, the whole motivation for this larger research framework is that compositional truth, it seems like something that essentially extends the theory. So you really added a truth predicate. But on the other hand, it's really a conservative extension. It doesn't allow you to prove any new arithmetical theorems. So by a theorem of Kotlarski-Krajewski-Lachlan, CT minus is conservative over PA. So you probably know this theorem if you know it in its classical formulation, that in every countable recursively saturated model of PA, I can find a full satisfaction class. So as you can see, there is very direct connection between satisfaction classes and truth predicates. We stated in the framework of truth predicates for now, because it's kind of framework in which this kind of questions were originally conceived. Okay, if you go to fully inductive variant, it's obviously not conservative. Why? Well, the proof is simply by give me an arithmetical proof, so proof within a model of PA. Then in CT I have induction, so by induction on the number of steps in that proof, I can show that any conclusion of that proof is true. Well, so assuming that I start from the axioms of PA. Well, this exact formulation depends on the exact proof system you formalize this in, but you know, we can say in natural deduction, any probable formula is true under any assignment, under any substitution of terms for the variables. In particular, I show that whatever is probable in PA is true, since compositional axioms are enough to show the Tarski biconditionals. So you can show that a formula is true if a sentence is true if and only if phi. So in particular, you prove full reflection. So whatever is probable is true. So whatever is probable holds. Right? So in particular, you get full reflection. Actually, you can iterate this reflection so you get new arithmetical consequences. This is just for the context. I expect most of you to know it. So now an important part of the context. The proof, if you formalize this direct argument, overtly uses pi1 induction for the formula with truth predicate. We can do better though. So give me this theory of compositional truth extended with induction full delta zero formulae. So add I delta zero for the formula containing the truth predicate. Call it CT0. As a matter of fact, it turns out that this theory is also not conservative over PA. So you can do better. It's enough to take delta zero induction. And as a matter of fact, so this is the context of the research we've been doing for a couple of years with people like Ali Enayat, Cezary Cieśliński, Mateusz Łełyk, Fyodor Pachomow was also an important contributor to this. There is a number of very natural truth theoretic principles. If you add them to CT minus, they happen to be all just equivalent to CT0. And the surprising thing was that you could start with a really number of very distinct principles. Each of them states something very natural about truth. And it's, as a matter of fact, it turned out that they all are pairwise equivalent. So, and they're not like cook up to be equivalent, that they were discovered to be equivalent with very distinct proof. So Ali and Ayat called this phenomenon like many faces phenomenon. So you can really characterize this theory CT0 in a very robust way in a number of very distinct manners. For instance, there's a very striking example. If you give me a disjunction over a finite set of arithmetical sentences, it's true if and only if one of the disjuncts, right? So if you state something like this, and as a matter of fact, when added to compositional axioms like compositionality for arbitrary finite disjunctions, this happens already to be non-conservative, and as a matter of fact, equivalent to CT0. And as a matter of fact, you can actually improve on this result and just say that a true disjunction has a true disjunct. This is already equivalent to CT0, right? So now, a very natural question. So you know that induction can be splitted into delta zero induction plus full collection. So how about pure collection? So Yeah, here's a
Excuse me, do you
slide.
take questions?
Of course, yes, please. Yeah, I should say that I said at the very beginning, so please do interrupt me. Yes.
Okay, so a naive question. So can I, using a Gödel sentence, a kind of a Gödel sentence, here, construct here a sentence which says about itself that it is not true?
Yes, I can.
And then you don't get a contradiction.
No, why not? Because why not? Because this sentence, if you construct it by diagonal lemma, this sentence does involve truth predicate, right? So it's not an arithmetical sentence, and we only assumed compositional clauses for arithmetical sentences, so it's stratified predicate. People do consider non-stratified. So actually, you have a sentence like this.
Yes.
But for this sentence, you cannot prove that this kind of equivalence holds, because this kind of equivalence holds only for arithmetical sentences, and this liar sentence is not one of those.
I see.
Right,
Okay.
because if you just plug into diagonal lemma, then you have to use this T predicate in order to construct this sentence.
Okay.
Right. Right. So this is a truth predicate working only for arithmetical sentences. So it's a very Tarskian situation. It's stratified. So actually, people in the field do consider. I think most people actually do consider self-referential truth predicates. Of course, they have to put some restrictions in order, precisely to block this, this contradiction. So typically, it's a sport of finding motivated kind of restricting how you restrict your compositional clauses, because if they were full, then of course you would get this, while still maintaining consistency. Okay, just a quick reminder of what collection scheme is. I don't think it's needed. So collection says if you give me a bounded set in a model, and for each element of the bounded set, so here's a model of PA, M, here's A. For every, you have a function, definable function that assigns for every element of a value, then you have a common bound of all those values. So classically, it is known that induction is delta zero induction, which says essentially that you can do coding of sets together with collection, which essentially says fragments of my model are finite compared to the whole model. Kay had asked the question. So I give you a compositional truth or full satisfaction class, and I postulate that it satisfies full collection. Is that a conservative extension? So I attributed the question to Kay. Actually, it's a very natural question. So I heard myself, for example, Kentaro Sato asking the same question. So if you see that actually many non-conservative principles all boil down to simply delta zero induction. So there's a very natural question any arithmetician worth their salt would ask. So what about collection? Right. So as you can see from the abstract, it turns out that collection gives you a conservative extension. So if you don't get delta zero induction, you have no coding, but you know that from the point of view even of functions involving the truth predicate, bounded segments of the model are kind of like finite, then this is still a conservative extension. This does not allow you to prove any new arithmetical theorems. Right. So already the proof strategy is kind of clear, and it was already suggested by Kay. So recall that a model is omega-1 like if it's of cardinality LF1, but initial segments are countable. So if you give me an omega-1 like model and you expand it with whatever predicate, then this predicate, this expansion satisfies full collection, why the argument is very simple, right? You have this very, very long model. You give me this very, very small initial segment. You take any function whatsoever, in particular a definable function. So the image is countable. So it's bounded in the model by regularity of omega 1. So you get collection for free. Okay, so now in order to prove the theorem, to prove this conservativity result, it would be enough to prove the following. You give me a model, let's say countable model of PA. Then I can extend it to elementarily to a model, to an omega 1 like model, in which I can find a predicate satisfying CT minus. So in particular, in that model, automatically collection must hold. Notice a couple of things. So by a theorem of Lachlan, any model of CT minus has its arithmetical part recursively saturated. So like there is no hope that any omega 1 like model will expand to a model of CT minus. As a matter of fact, in a model of CT minus, you always have an undefinable class. So an undefinable set, like undefinable set cofinal in the model, whose initial segments satisfied are coded. So are arithmetically coded. So in particular, if you start with a recursively saturated, rather classless omega 1 like model, then you also have no hope for satisfying full collection. You have no hope. Sorry, you have no hope for finding a predicate satisfying CT minus. So you really have to cook up such a model. It's not that you will find it in any model in any sense. So our goal is this: you give me a model, a countable model M. I want to find some extension M prime, and in this M prime, I want to find the truth predicate that satisfies compositional clauses. Okay. There's one of the strategies that doesn't work. So how do you normally produce omega 1 like models? By taking chains of end extensions. So if you could start from a model of CT minus and maybe extend it to a model of CT minus and keep repeating this, just by finding an end extension, not necessarily elementary in any sense, then you could in the limit get this omega 1 like model. So this is one like obvious strategy. Unfortunately, first of all, notice that this strategy would work. So for the first thing is that such an extension, so if you have a truth predicate and you end extend it to another model with a truth predicate, then as a matter of fact, on the arithmetical part, this extension is automatically elementary, right? So if you start with some formula, arithmetical formula phi of 8, and in the model, this formula is true. So in the extension, it's also true. This is an atomic fact. So since the other model is also a model of truth, of the truth predicate, in the extension, phi of A also holds. Okay. So this is an elementary chain in the models of PA. So actually, this is a good sign. Notice also, if you just look at the axioms of CT minus of the compositional truth, then modulo arithmetical statements, they happen to be pi 2. So as a matter of fact, this will be preserved in the unions of models. Right. So if you have a truth, if you have this end extension property that any model can be end extended, let's say any countable model can be end extended to a model of truth, then the conservativity of collection would follow, even though there is no elementarity here, right? So you can like cheaply get this elementarity. You don't get elementarity, but you cheaply get collection without getting elementarity of the extension. So this really almost works, and this will be like the general idea of the actual proof. So this doesn't work because there are no end extensions necessarily. So you can find, actually it was found in a paper of Smith in Animals in the late 80s. There can be a model with a satisfaction class, with a full satisfaction class, which cannot be and extended to a model with a full satisfaction class. Right, so it can happen that you have a model M with some class T inside, such that you cannot and extend it to a model which also has a satisfaction class, and I don't care about like elementarity of this extension or any other kind of link between those models. Why? So this is part which you have to kind of believe me. Using, for example, proof of a Naiad-Visser or using earlier methods of M-logic, originally employed by Kotlarski, Krajewski, and Lachan, you can, in fact, show that you can have very pathological truth predicates. So you can cook up a model, a countable model, such that in the model there is something that's, according to the model, is an arithmetical formula, such that for some element of the model, it is true that this defines a function below A. This function happens to be onto the whole model. So you have a surjection from the initial segment of the model to the whole model. Under truth predicate. Right, so notice that if you assume this, so this is a true statement, like according to the model, this is a true sentence, this is a true sentence. So if you take any extension of the model, which also satisfies compositional truth, those are arithmetical, those are like atomic formulae from the point of view of truth predicate, right? Something is true, so it also happens to be true in any extension of the model. So this also holds true. Now take any element that's new. So it's in particular, it's above all the previous elements. So now look, it is true that for all x less than a, there exists the unique, I'm sorry, it's true that for all y, there exists an x smaller than a such that phi of xy holds. So using compositional conditions, in particular, if you plug in here C, it's true that there exists x smaller than a, such that phi of xc holds. Right, so here's your model M. Here's this A. Maybe this will be M, this will be M prime. So this is our end extension. You get C here. So for each Y, in particular for C, there is an X, call it A prime, such that this function phi sends A prime to C. Okay, but look, this is an end extension, so this A prime actually is an element of M. It's an old element. By this first clause, we actually know that this A prime has a unique value T under the mapping phi. Okay, but this directly contradicts functionality of the formula phi, because A prime is supposed, like C is supposed to be the only element such that T of phi A prime Y holds, and D on the other hand is another such element, which is a contradiction.
Bartek,
Yes, please.
can you say something about this formula phi?
How do you get it?
Yeah, I mean, I don't know if there's something brief you can say about, yeah, how do you cook this thing up?
Okay. If you have an Naiad-Visser construction, like basically for any formula that give you that, you know, like in general, if you see the constructions for okay, so if I can, like, for example, invoke a concrete theorem. So a concrete theorem would be that any subset of a model such that X expansion of that set is recursively saturated is definable by some formula under some truth predicate. So that's, for example, one reason why I can get this sentence. So essentially, up to a first order theory of a formula that a set is supposed to satisfy, you can assume that the set is definable with a single formula. For example, by using an Fisher, you can starting with any formula that has no like obvious finite local reason to define some concrete set. So for example, it's not a standard formula, or it's not something resembling a standard formula. You can really set pretty much any value to that formula. I'm sorry, I know I'm being vague, but there is a whole, like proof why. But the moral is that you can essentially, given a set, pretty much make an arbitrary formula define that set in the model of truth predicate, if there are no like obvious obstructions. Okay.
So is there anything special about the model here? So
no.
Given any countable recursively saturated model and any appropriate set, you can find a truth predicate that defines it in an appropriate way.
Yes. So in particular, for any countable rec saturated, for any A subset M such that MA is recursively saturated as a pair, there exists a phi in M, there exists a T such that this satisfies CT minus, and like A is the set of X in M such that T phi of X.
Right. Okay. All right. Thank you.
So literally any set up to a first order theory can be defined by a formula, by some truth predicate. And but the proof requires you to look closer at the NAF reconstruction. So for example, I mean, I can send you some papers where it's explicitly proved. So we reproved it, for example, using NAF Fisher. Originally, it was a result in the same paper by Smith.
Okay, thanks.
Sure. Please do ask questions. Okay. So we have a counterexample. So we have an abstraction to the existence of end extensions. So now the naive question. So you take a model in which this particular abstraction does not impede your construction. Are there any other abstractions? And as a matter of fact, after a couple of years thinking of it, it turned out that the counterexample found by Smith is essentially the only counterexample to the existence of end extensions. So the end extension can break down because you have. Notice that essentially what happened in the previous slide was a brutal violation of collection under truth predicate. So in particular, in any model in which collection holds, you cannot have a formula like this. So you better exclude those kind of counterexamples if you plan to build a model of collection. And it turns out that if you exclude this kind of counterexamples, then essentially you're done. So more precisely, consider the axiom of internal induction. This is the following sentence. So you give me a formula. If this formula is true about 0, and it's progressive in the sense that if it's true for X, then it's true for the successor, then it's true for all elements, for the elements. So this says every set definable with a non-standard formula under truth predicate satisfies induction. I realized that I didn't put the crucial theorem here. So theorem, and essentially it's also in KKL, in Kotlarski-Krajewski-Lachlan. CT minus plus internal induction is conservative over PA. So whereas induction for the formally satisfying truth predicate is like very non-conservative principle, if you say that every formula satisfies induction internally, then this doesn't bring you any arithmetical strength, which is crucial to our proof, and I think I forgot to put it on slides. Okay. So now we have a proof strategy. You give me a countable model now with internal induction. Then I can find a proper end extension. Also satisfying internal induction. Right. So we're essentially done. Because you start from any model M of PA whatsoever. So there are no restrictions on the theory. It's countable and recursively saturated with all loss of generality. So I can find a predicate T0 satisfying compositional truth plus internal induction. By the theorem, I can end extend it to M1 T1, satisfying the same theory. I keep extending it. And recall that the extensions are elementary in the arithmetical part, so the arithmetical theory doesn't change. Recall that it's preserved in the limits. So M omega T omega is automatically a model of CT minus plus internal induction. In particular, it's automatically a model of PA because the chain is elementary in the arithmetical part. I keep extending it throughout countable ordinals. Finally, I get to model M omega 1 T omega 1. It's obviously omega 1 like. Again, CT minus plus internal induction is preserved in the unions of chains, or generally unions of models. It doesn't have to be end extensions even. So what I get is a model, is an omega 1 like model of CT minus in particular, starting from an arbitrary, completely arbitrary arithmetical theory. So for any arithmetical theory, for any extension of PA, I found a model of that arithmetical theory, which is omega 1 like, has compositional truth inside. And well, by the fact that it's omega 1 like, it's also automatically satisfies collection. So that's the main strategy of the proof. So of course there is the not so easy task of proving that actually those end extension exist, but I hope that the whole strategy, my basic aim is that the general strategy at least is clear. So you would like to produce this kind of omega 1 chains of models of CT minus. Normally you cannot because models of truth don't have end extensions typically. You find a slightly stronger theory, and then you, with some effort, you prove that those models do have end extension, but on the other hand, those models, this theory is conservative over arithmetic, so you can start from any model and push the chain like this. Is there any question? Right.
Yeah, just a reminder, question for reminding, because I...
Sure.
What does this minus here?
That,
what does it minus indicate?
That I don't assume induction for the extended language.
Oh, I see.
That's pure compositional clauses. I don't have any induction.
Okay.
Like I do have some induction in this form, right? This is some form of induction, but it's very modest form of induction in the sense that I can edit for free. That it doesn't give me any arithmetical consequences. Are there any other questions? Okay. So let's proceed. Okay, so I think some of you will like have this feeling of relief because from this point on, I will actually work with satisfaction classes, so the rest will for the context. Instead of a unary predicate, we'll have a binary relation S of phi alpha. Phi will be a code of an arithmetical formula. Alpha will be an assignment in the sense of the model. So it will be a function which takes three variables of phi and assigns some elements to them. We will assume that the satisfaction class satisfies Tarski compositional clauses, actually not necessarily on the full model, but on sets of formulae closed under direct set formulae. We'll also assume that they satisfy some strong regularity properties, which I will definitely hide under the rug. Those regularity properties are actually technicality needed both for the proof and to assure that they really corresponds to the models of truth, because the link between truth and satisfaction is not as clear cut as I would like it to be. I can also treat satisfaction classes axiomatically. If I have full satisfaction class with no induction axiom, I would call it CS minus. If I have a cut in my model, then by writing CS minus restricted to I mean that S satisfy compositional clauses for formulae phi whose syntactic depth is in I. So it's not that phi is in I, not necessarily phi is not only for phi which are small, but only for phi which are potentially big but for stupid reasons. So I can have a formula which is very, very big, but because for example, it contains very, very big variables. So variables with very big codes, I don't want it. I just want to look at the syntactic structure of the formula. If the syntactic tree is small, then I want to have compositional clauses for it. And crucially, this has to work for all assignments. So the compositional clauses are really quantified over arbitrary assignments. So it works. It's compositional for right.
So this depth is the height of the syntactic tree.
It's the height of the syntactic tree, right? I don't count terms. I count only. Right. Do I recall correctly that I have 1 hour in this seminar? So 20 minutes now.
Yeah, if you.
Okay. I just want.
So there are options. If you need more time, we can either.
No.
We can go on 10-15 extra minutes. It's okay.
I always try to avoid this kind of cruelty to the world. So no, I'll stop when I stop. I stopped at the moment that I was supposed to. Okay.
Bartek,
so the proof of
Can I ask a stupid question?
Yes, sure. Always.
To me, satisfaction class and a truth predicate is basically the same thing. What am I confused about?
Okay, so this is not stupid question. This is perfectly fine question, but it has like obnoxiously technical answer. So as a matter of fact, we don't know whether, given the model with satisfaction class, it has a truth predicate. So if you try to prove it, so like, of course, you'd normally try to define it like this, right?
Yep.
Like the problem is, what exactly are your compositional clauses for quantifiers? So if I start with exists x as the phi of x, and I have alpha here. Yeah, the problem is so the problem is this. So I have a formula phi of v. Let's say that this is a assignment which sends v to 0. And in order for this to make sense, you would like to say that this is the same as saying that phi of 0 with an actual number here is satisfied under the empty assignment. But as a matter of fact, this is not provable from pure conditions of the satisfaction class, So then this equivalence can break down. So then you have to put in some, plug in some regularity conditions in order to fix it. And it turns out that those regularity conditions are needed in the proof anyway. Right? I'm sorry, the answer is unpleasant.
Okay, I see. Yeah, I did not think that. I see they're just annoying technicalities. Okay.
Right, right.
Thank you. I see. I see. Okay.
So Roman, you had a question, right? Or not?
Before you move on, can I ask, going
Okay.
the other way around, is that okay? Like if you start with a truth predicate, then
Not necessarily. Not necessarily for the same reason. Like for essentially the same reason.
right. So I would think that you could sort of define S of phi alpha to mean that the if you assign alpha, if you follow the assignment by alpha, then that was true in this truth predicate phi. So
Yeah, but suppose that you have a very pathological class such that T of phi is true, but T of phi of 0 is true, but T of phi of 0 plus 0 is not true. So then how do you assign S of phi of V where V goes to 0? So is that guy correct or is that guy correct? Right? How do you produce from such a pathological class, how do you produce satisfaction for assignments? You could, okay, so you could have some systematic preference, but then you get into new technicalities and this kind of things I just want to avoid.
so you need some sort of something that says that your truth predicate behaves. This is the
Regular, yes. I need some regularity conditions, which I do assume, like which I put there. So they are assumed, so we're all safe. Okay.
Bart, so this brings one question. So could you define this regularity as this possibility of showing equivalence? That the satisfaction class is regular if and only if there is some definition of truth from it, and truth is regular if it goes the other way. You don't, without specifying how it's done.
That's a very good question. I don't know. I mean, but I haven't thought about it. It sounds like a possibly good definition. I can think about it.
All right.
But it's a very good question. Okay, so the proof will come in two steps. So the first step is you start with a model of full satisfaction class with internal induction. Internal induction still makes sense for satisfaction classes. Then you can find an end extension, sorry. So this, imagine there is a small e here, and actually there is no equality here. It's a proper end extension, such that, first of all, in the extended model, so you start with a model M with satisfaction class S. You can find an end extension M prime, such that in the extended model, you can find a satisfaction class which works fine for all assignments and all formulae from M. Right? So if you have a satisfaction class satisfying internal induction, you can say what it means for the old formulae to be true about new assignments, about new elements. First of all, and second of all, you can also assume that this M is semi-regular in M prime. So for any A in M, so if you have this is M, this is M prime. If you give me A from M and some function, which is coded in the model, in the big model, which possibly sometimes spills out very big values, sometimes small. If you look at the values of the function in model M, then actually they are bounded in M. So a function coded in M prime, defined on a small set, may sometimes shoot out of the model M, but if you restrict to values which actually are in M, then those values are small in M. So the crucial part is the first one. The second part is something that I think can be like weakened in the future, but it's a technical condition that's crucially used in the proof. So given a satisfaction class, you can extend it like so that for each formula can be evaluated on the elements from the new model. So you can kind of extend it in its width, not in its height, in a sense. I'll get to the proof in a moment. So let me start with the second lemma, so that I want to complete the proof. So assume you have a satisfaction. You have this situation, right? This is M, this is I. So this was our M, this was our M prime. And you have a satisfaction class that works fine for the formulae from here and arbitrary assignment. And arbitrary assignments. Assume, moreover, that I is semi-regular in M. Then you can actually extend it, the whole class, you can extend it to all the formulae. So you had a class that worked for small formulae or formulae of small, actually, syntactic depth and arbitrary assignments. You can extend it so that it works for all formulae in the model. Assuming that this model, this cut I of the formula for which your satisfaction class works, fits nicely into the model M. One piece of like warning, because the semi-regularity, because other than that, this proof sounds like an obvious proof strategy. You have a model, you have a truth predicate here, you end extend it so that this truth predicate works for old formulae with new assignments. So you first stretch it from left to right, and then you stretch it in the width so that it actually covers also the new formulae. So that now it covers, it's now a model of CS minus in the end extension. It turns out that in order to do this, we actually need some kind of regularity, because without it, I mean, I'll go to the proof in a moment, but of course I'll have to be to omit many details. But if you omit the semi-regularity assumption, even if you assume that I is an elementary submodel, then simply the lemma, this upward extension lemma, fails. So you can have a model, a cut of formulae on which some satisfaction class works. This cut can be very closed under functions. It can be even an elementary submodel. And still you can have a possibility that you cannot extend, like prolong this satisfaction class so that it works for all the formulae. The counterexample we have was in our paper with Roman, and it actually uses disjunctions with stopping conditions. So it's kind of involved. And then crucially, we use a pair of models such that the bigger model codes on cofinal omega sequence for the smaller model. So it's very non-semi-regular. So this counterexample was what actually inspired me to add the semi-regularity condition. And actually it turned out it works. Okay. So now I'll try in the last 10 minutes to very briefly sketch the proofs. I know I'll fail in it, but. So how do you extend your model, extend your satisfaction class to the end extension to all valuations from the end extension? You take your model of CS minus. For every formula, you can introduce the set defined by this formula. So define a predicate as phi, such that S phi of alpha holds if and only if phi is satisfied, alpha is satisfied by phi. In this way, you slice your truth predicate, your satisfaction class, into a countable family of predicates. If you look at internal induction, this exactly says that this model satisfies full induction. So by Magdalena-Specker, you can have a conservative elementary end extension. So you prolonged each formula independently. You set for each formula independently what it means to be satisfied by elements from the next model. And then you essentially glue them together. You check in the obvious fashion. So you repeating this condition, you reintroduce your predicate S. It works. It is compositional. It's defined for the old formulae for all valuations. And you essentially check that by conservativity, you get semi-regularity of the extension of the models in the arithmetical part. Because notice that this is conservative in the extended language, so it's actually not conservative in the arithmetical part, but it's semi-regular in the arithmetical part. And then you glue this together and check that what you get satisfies compositional clauses. I know this is very sketchy. How do you extend upwards? So suppose you have a model, you want to define it for all the formulae. Actually, you use the proof that Fyodor Pachomov used a couple of years ago to show a new proof of conservativity of a new construction of a satisfaction class.
Bartek, this could be a silly question, but how do you know the extension is not conservative?
If you both models are recursively saturated.
Oh, because of that, right?
Right. So in particular, that M primes has coded.
Right. Yeah.
Coded satisfaction class that works for formulae of that at most C. In particular, if you cut this class to a model M, this will be a inductive.
Right, because I was thinking that the question, why is it one of those F5 alpha undefinable that you code all of them, and it's somehow obvious that there must be one that's not definable?
It's not obvious, but it's true.
All right.
It's not obvious, but it's true. Okay. Yeah. How can you know? You kind of you can show it. You can show it, but the argument kind of is similar combinatorics to disjunction with stopping condition. But you can actually do this. Okay. So how that extend to
Bartek, can I ask?
Yes,
so there's there isn't a lot of time left, and so I would like to hear the argument. And so I was we actually don't have a speaker next week, so if you're interested, you can continue next week if you would like to be able to get through more material, but it's up to you if you think you can. I don't want you to feel like you have to rush. So
no. That's actually
I second this. I second.
I third it. Yes, I would like to hear it in more detail, and so if it's all right with you, we would love. I think we would love to hear it more slowly next week.
Sure. That's a great idea. Okay. So that's a perfect place to stop. I'll revisit the first lemma. Try to give 15 minutes of short introduction of what happens last time, so that I know that I was kind of speeding up at the end, so that I'll try to make up for it. So I think it's a very good moment to stop. So for those of you who want to be part next week, right?
Yes, just one question. Can you here get a soundness theorem? That means everything which is provable is true.
Absolutely not. Absolutely not. This is not conservative, right? Absolutely not. If I do, right, if I can show that whatever is probable is true, so I can do this. I can prove it with if I have induction for the truth predicate. So in CT, you can show this. In particular, from this, it follows, since you have equivalences for arithmetical statements, you can actually show full reflection from this, which is of course not which of course means that this is not conservative over PA. But CT minus as a conservative theory doesn't prove it. CT minus plus collection as a conservative theory doesn't prove it. CT minus plus internal induction as a conservative theory doesn't prove it. Okay, in particular, that proof shows that you cannot prove soundness of PA just using collection on the proofs. So the argument has to use like the natural argument uses pi1 induction, you can actually make an argument using delta zero induction. This shows that you cannot have an argument using collection. Does it answer your question?
I believe that it does. We'll have to think
Yes.
about it, but I believe that it does. And yeah, intuitively, if you had something like that, you might prove the consistency of the theorem, the theory in the theory itself, which is impossible.
Yeah, sure. If you have reflection, then in particular, if 0 equals 1 is probable, then 0 equals 1, which of course means that by contraposition, that it's not probable, right? So you get actually a compare. And much more, right? It's full reflection, so it's much more than con, actually. Possible.
Yeah, I have a question, a naive question.
Yes, please.
Yes, no, in these proofs, recursive saturation plays a big role.
Yes, definitely.
Now, naively, I would guess that I could replace recursive saturation by primitive recursive saturation.
Mhm.
Right?
But those are the same, right?
I would think, because, pleonasm would work.
By Craig's trick, though, those are the same, right?
But
They can
now,
actually,
go on. You're saying something.
yeah, because you can actually, if you have a recursive type, whatever recursive type, you can actually take a number of steps needed to compute the fact that this formula is computed by this machine, and replace that formula by its idempotent version. And here you code the number of steps a machine needs to show that it accepts phi n, right? So you can make any for any type, you can make an equivalent type, a logically equivalent type, such that it's much easier to recognize whether a formula is in that type.
Yeah, so that's like the old Vought pleonasm trick. But now, if you take the Gregorchik hierarchy, right, for primitive recursive functions, can you push this argument any further down in the hierarchy?
Okay, right. So I guess that actually this argument pushes it down very low, right? Because in order to check, given a machine, and give her the actual explicit number of steps I have to compute, then in that number of steps, checking whether the machine computed at the end of the day phi n, it's a polynomial problem, right? It's a feasible problem in the number of in this huge formula. If as an input I'm given explicit number of steps, I don't have to make any.
So intuitively, I mean, I don't have a good intuition with this. Intuitively, then where does the power of this notion of recursive saturation come from? What's the magic bullet in there?
From the saturation part, right? I mean, like not from the, not from the. So recursive saturation is kind of unhappy, maybe nomenclature. What you really mean is that, like controllable types are there, which imposes extreme amount of uniformity on the model. So now your model, basically, if it were an order, it basically looks like Q. So anything that you can do there. And then you can, by playing around with so in particular, of course, the answer is that the key part is resplendence. If you go to resplendence proof, then you really are playing around with the notion of you're given a theory, and then you're looking for probable fact, like if there is no probable reason why this theory cannot be realized, then actually piece by piece you can realize it. So that would be the high level answer.
Right. I just wanted to add to it for Ken that the power of recursive saturation is really resplendence. This is just what Bartek just said, and resplendence in the original formulation doesn't involve any computational elements, but it becomes much weaker. But recursive saturation gives you resplendence in the countable case, but you lose it in uncountable. Actually, recursive saturation becomes very weak. But except rather classes, recursively saturated models do not have satisfaction classes. All this breaks down for uncountable models, but doesn't for resplendent.
Well, thank you guys. I mean, there's the magic in this notion. It's just, it's impressive.
Yeah, of course I do agree, right? I
agree.
So we've already started questions, but before we take, there's time for more questions. But before we do, let's thank our speaker because this was a great talk. So I really enjoyed it. Thank you, Bartek. Moji.
Thank you.
Do we have any?
Speak at this on this?
Chaim had a question I saw.
Just
go ahead.
in which journal has all this been published? Whatever has been published.
So this is this particular part of this work was preceded by a paper in Annals. So actually, which was local collection and something blah blah blah, joined with Mateusz Wełek, which actually was our first attempt to prove conservativity of collection, which got stalled. So essentially, that part establishes the first claim. And now the second part was the lemma of upwards extension was figured out in the last autumn, I would say, like late November, maybe, yeah, late November, I would say. So it's still, I mean, there is a working note where the details are written up because there are lots of them, like all the regularities and so on. But I hope that I'll write down the paper in the next 2 months, let's say. So it's like so it's very fresh.
Excuse me, I don't know. What is the APAL?
Annals of Pure and Applied Logic.
Oh yeah, okay.
So that's the first part. That's claim 1, and the second part, and it's actually from a couple of years ago. And the second part, I hope, will be published in this year. I mean, it will be submitted in a month or so, like in a month or so.
Other questions? Okay. All right. So let's thank Bartek again. And as we just discussed, Bartek will come back next week and continue and finish the presentation. So same time, so same link and everything. So see you all.
It's always great to be at this seminar. Thank you so much.
Thank you. This was great.